The bond angle in ethers is very similar to that found in water and alcohols. For example, we have this hydrogen-oxygen-hydrogen bond angle of 105 degrees. And then if we look at this alcohol, we've basically replaced this hydrogen with the methyl group. The methyl group has increased steric demand, which will widen this bond angle to alleviate that steric strain. And then moving on to an ether, there will be two carbon-based groups on both sides, and therefore the bond angle will be even wider. Most oxygens of simple ethers are sp3 hybridized, and that's because it's making two sigma bonds and also has two lone pairs that are both localized and therefore count towards the steric number because those lone pairs go into a hybridized orbital. So this one has a steric number of 4, leading to it being sp3. But there are some ethers that are sp2 hybridized. For example, if we look at methyl vinyl ether, the oxygen here is sp2 hybridized, not sp3. And the reason for that is because of the neighboring sp2 hybridized carbon. So this carbon has a p orbital overlapping with the p orbital on the next carbon, forming the pi bond. And then because of those p orbitals, one of the lone pairs on the oxygen will also exist in a p orbital. If that happens, then the neighboring p orbitals can overlap, and there will be increased electron delocalization, which makes those electrons even more stable than placing them in a hybridized orbital. So as a result, this oxygen is only making 2 sigma bonds and has 1 localized lone pair that counts towards its steric number. So it has a steric number of 3, leading to it being sp2. So again, all 4 electrons, 2 from the pi bond, 2 from the lone pair on oxygen, are delocalized over that 3-atom system, making those lone pair electrons more stable. So another example of an oxygen, which would be sp2, would be if the oxygen of the ether was right next to an aromatic ring, right? So it's right next to an sp2 hybridized carbon with a p orbital. Therefore, one of the lone pairs on this oxygen will also be in a p orbital, and this oxygen will be sp2. Let's look at boiling point. So if we recall, alcohols have relatively high boiling points compared to other similar molecular weight compounds. And that's because alcohols hydrogen bond, which is the strongest intermolecular force. Right, so that's why water, for example, has a higher boiling point. So this is an example of a hydrogen bond, and it's a intermolecular force because it's within or between 2 molecules. And then we say that the hydrogen bond has a hydrogen bonding donor and an acceptor. So the one that has the hydrogen, this one is the donor, right? And then this lone pair on the other is the acceptor. Well, for ethers, they can hydrogen bond, but they cannot hydrogen bond with another ether, only with an alcohol molecule, right? So here's an example of a hydrogen bond occurring with an ether, but the problem is the ether can only act as the acceptor. It doesn't have a hydrogen directly attached to an electronegative atom to act as the donor. So as a result, small molecular weight ethers like dimethyl ether will be miscible with water because they'll be able to form hydrogen bonds with water or other small molecular weight alcohols. But ethers themselves, we say that their boiling points are lower because they don't hydrogen bond with each other. So they don't hydrogen bond with another ether, right? So therefore they don't hydrogen bond unless they're mixed with something else that can act as a hydrogen bonding donor. If we look at some boiling points, notice that dimethyl ether has a low boiling point. In fact, it's a gas at room temperature, not anything like ethanol, which is a liquid with a relatively high boiling point. And that's because there's no hydrogen bonding going on between two dimethyl ether molecules. And this one relies on a dipole-dipole as its strongest intermolecular force, which is much weaker than a hydrogen bond. So the boiling point is very low. However, as the alkyl groups get larger in an ether, so going from methyl to ethyl to propyl, for instance, we're going to notice a dramatic increase in boiling point. But that's just due to larger molecules having increased London dispersion forces. Ethers are common solvents in organic reaction. That's because they are polar aprotic, which is great because it can dissolve lots of polar compounds, whereas it's not protic like an alcohol, which can possibly interfere in reactions. So here are some common ethers that are used as solvents in organic reactions. They have lots of things going for them. One is they have relatively low boiling points. So for example, diethyl ether's boiling point is only 35 degrees. THF is something like 65 degrees. So they have relatively low boiling points. There's two oxygens here in dioxane, so it's a little bit higher boiling point, right? But especially diethyl ether and THF, those are very low boiling points. They're easily removed through rotary evaporation. Ethers are also fairly unreactive. You'll see when we study reactivity of ethers that there's not a lot you can do with simple ethers. There's quite a bit you can do with epoxides, but that's a different type of ether, right? So these simple ethers like diethyl ether and tetrahydrofuran, they don't do a lot in terms of reactivity. They are great solvents for when you have metals that are positively charged. So for example, this is the formation of a Grignard reagent in order to do the Grignard reaction. And it's great to use an ether solvent because the oxygen's lone pair, which has a slight negative charge through induction, is stabilizing the positively charged magnesium.